I'm here today to talk about, well, the challenge of developing post-classical applications with mostly quantum computers. I'm from the University of Technology, Sydney, from the Centre for Quantum Software and Information, and also the Australian Centre of Excellence for Quantum Computation and Communication Technologies. This talk won't be about any one paper, it's going to be about many. But very broadly, this is like the large list of people I've been working with on this topic. So mostly this is work being done with Ashley Montanaro, Dan Shepard, and Ryan Mann, and Richard Joza, and then and Austin London and Tim Ralph, and then the team from Google. So when someone puts the word challenge in a title, it means they don't know the answer. Just so you know. And I don't know the answer to this question, and this is very speculative. You would have had a sense from Han He's talk that one of the real issues we're facing from a theoretical viewpoint, I'm a theorist if you didn't realize, is that developing applications in this near-term space means we don't get to fall back on a lot of the tools we're used to falling back on when we're talking about developing algorithms. Okay, so we have to deal with things like noise. We have to deal with the limited size in our computers. We have to deal with limited depth in our computers. This makes developing things hard. So with luck, the way that the field will evolve over the next 5 to 10 years is that we'll sort of hit this sort of 50 qubit-ish mark over the next 12 months. I think I said the same thing 12 months ago at a talk at IBM, and I'm not sure we're quite there yet, but we're aiming for that in the next 12 months, hopefully we'll be seeing reliable 50 qubit devices that people will be able to see actual data about in the near term. And hopefully the sort of fidelities we're talking about, at least for most of the gates, is something on the order of 99 point something % fidelity. And this is roughly around the sort of scale we're also going to expect to say we can reliably have a fault-tolerant qubit in something like the surface code. Now, you could sort of argue this is essentially like a classical quantum frontier. And I'm going to talk a bit about how you can sort of think about this through the rest of my talk. But as you hit that sort of 50 qubit threshold, with that sort of fidelity, you can begin to think about doing computations that classical computers can't do. I'll give you a bit of a sense of that in the talk. Now, beyond that regime is where things get really interesting. So, you can sort of talk about doing these so-called quantum computational supremacy experiments at around that 50 qubit-ish mark. But what happens in between 50 qubits and 10,000 qubits? And what can we do in that space? And that's the really exciting problem, which everyone is pouring a lot of effort into right now. Some of the standard things, or the sort of questions that people are thinking about is like, how do we do error mitigation without having full fault tolerance? So the overheads for doing full fault tolerance, as we heard about this morning, are pretty high. Okay, so under 10,000 qubits, we can't really expect to have particularly large logical circuits. So we need to think about, is there a way we can fall short of having full fault tolerance, but still to do some interesting computations? Can we have notions of sort of testable quantum advantage in this regime? And I think the answer is yes. Then the question is, what sorts of problems people are thinking about is like approximate optimizers, variational algorithms, things like that, like QAOA, quantum, and then variational algorithms for chemistry, but then also direct chemistry and other sort of small quantum system simulations. That's a thing which is obviously one of the biggest and most interesting topics in this space. So, and other stuff that we have no idea about yet, but with heaps of people pouring heaps of effort into this field, hopefully we'll begin to get some more interesting answers. So this is an interesting space, and we have to get way up here or beyond to really talk about fault-tolerant quantum computing in a more serious sense, and that timescale is more like 10 plus years away. Now, also really interestingly, there's been a lot of commercial interest flooding into the field because we're beginning to talk about how can we develop applications in a space where you might actually be able to outperform the existing computing paradigms that we have. And as you can see, as you probably have all heard, Rigetti, for instance, have put forward $1 million prize for a theoretical demonstration of applications which could be performed on their devices, which could outperform classical computers. Just this week, Airbus announced a similar challenge, except in this space they want to see applications which have been explicitly developed for aerospace type applications. So it's clearly an interesting time, and there's clearly a lot of financial incentive for developing in this space now. Then you got to ask some more serious questions, like how can a quantum computer be better than a classical computer? And that's, I mean, as a theorist, typically my answer would be like, well, we want to like have circuit lower bounds. That's what we want to prove. But in reality, the question's a bit more complicated than that. So, the question you want to sort of ask are like, are there quantum applications with some sort of legitimate value, ideally, that are faster on a quantum computer? And that's sort of, in some sense, the strongest sort of criteria you could hope for. Are they more accurate? Is another question that you might want to consider. Okay, and so there's been some discussion about QAOA delivering more accurate answers than those, for instance, that might be delivered by a classical computer, but there's still a lot of work going on in that space. And the third criteria, which I think is one that as academics we struggle with, is it more cost effective to do the computation on your quantum computer than it is on your classical computer? Now that might sound kind of absurd given the cost of like a Dill fridge, but it's not that absurd when you think about the cost of developing applications. So if this classical application requires you to hire 20 of the best software engineers who've just graduated from MIT versus one person who can quickly code up a thing that you can run on a quantum computer, it might actually be significantly more cost effective to take the quantum route. And that's, I think, the question that a lot of companies are beginning to ask. Is there a way of developing this application faster and cheaper on a quantum computer than going via the classical supercomputing route? Okay, and then, can you beat classical computers? And can any of these criteria actually be satisfied in the near term? And I guess that's the big open question, and that's why there's $1 million prize from Rigetti for this sort of question. Okay, now let's talk about, so that's probably the last point in this talk where I'll talk about anything that remotely sounds like something practical, because the rest of the talk is going to be about complexity theory. So really excitingly, this year, there was a paper published in Science demonstrating a clear separation between quantum and classical computing when you think about low-depth circuits. And from a theoretical viewpoint, this is a super exciting result, because what it demonstrated was that you can have an unambiguous separation between quantum and classical computing, albeit in sort of the low-depth paradigm. And Hanhi mentioned this earlier, but Bravi, Goss, and Koenig showed that the 2D hidden linear function problem can be solved in constant depth with a quantum computer, but requires at least log n depth classically to be able to be solved. Now, what does this mean in terms of outperforming classical computers in the near term? Probably not that much, because you can imagine having a maximum digital runtime on a classical computer, and it's huge. This is not to scale. That's like a long time, because memory can last a long time classically. You have sort of a logarithmic type scaling classically, but a constant scaling quantumly for this sort of problem. And you have to also think about the fact that the maximum quantum runtime decreases with the size of your system if you don't have error correction. So, the separation here is not massively practical, but from a theoretical viewpoint, it is super interesting. And it gives us a bit more of a sense of what sorts of structures we should be hunting for when we're looking for a speed up over classical computing. Now, and that's essentially what I'm going to talk about for the rest of the talk, like what sort of structures, the sort of things we should be looking for. Now, ideally what you want to really get a significant advantage over a classical computer is a scenario like this, where you have a hugely diverging runtime for a quantum and classical computation, or for solving a problem either on a quantum computer or a classical computer. So you want, for example, like an exponential blow up in the runtime classically, whereas in the quantum case, it stays relatively low. Okay, so one example, which is what I'm going to talk a bit about, is when you look at the problem of just simulating a random quantum circuit. Okay, so what you're hoping to be able to show is that you can land there with the physical system in that little tiny triangle, where you can show that you can make your system work there, which is underneath the blue curve. The classical runtime explodes, but still inside the window before your quantum computer turns into a pumpkin, essentially. Okay, and there are some key issues with demonstrating anything at all that looks like that. The first one is, are quantum computers super polynomially more powerful than classical computers? And this is essentially the biggest question in quantum complexity theory. We still don't, this is probably something we can't resolve easily. It would separate P from P space, but we don't know whether quantum computers can definitively, in an unambiguous way, outperform classical computers. When you're talking about, are quantum computers able to perform computations that can't be performed efficiently ultimately on a classical computer? The other question you have to confront is for which specific computations do these runtimes diverge? Like what families of things do you see this rapidly diverging behavior? And are any of those things, for instance, interesting problems, or are they just things that you only see with random type circuits? And then finally, can you do any of that without fault tolerance, really? Okay, so this is a hope and a prayer that you can actually get underneath that red line and underneath the blue line and land on that green line at the same time. That may not be a thing that can actually ever happen in practice, okay, without fault tolerance. Now, as a theorist, once you identify such an application, there's a whole bunch of really interesting things we should think about too. Like, how do you minimize the gate and qubit count for any such application? How do you understand the influence of errors in such things? How do you mitigate errors in such applications? And finally, how do you improve the classical simulation algorithm so you really understand the nature of that classical curve? And these are the sorts of questions we now are beginning to have to really think about when we're developing applications or algorithms for quantum computers. Okay, so I'm going to talk about a specific family of such applications, and these are those which come from the random circuit model, random circuit sampling problems. Okay, so the goal of these, and I'm assuming many of you are familiar with a lot of this, so I'm going to go pretty quickly, but I'm going to try and give you a sense of the theoretical background behind these problems. So the goal, broadly speaking, is the goal is specifically to output samples x, which is going to be like a bit string or something like that, with probability p of x which has been defined by some random circuit. The general idea is to bound the complexity of this sampling task via studying the properties of this probability distribution p of x directly. Okay, and there's some reasons for that which I'll get into later. And the general hope is that if p of x is complex enough, then classical computers can only ever simulate sampling by directly computing p of x. And so we're trying to come up with a set of problems for which the only really viable classical strategy is to actually compute p of x, but that p of x is going to be a really hard problem. The intuition as to why this is possible and why it's possible in random circuits is that random circuits quickly develop long-range correlations in a way that others don't do it. And what's really important about this is they do so in an unstructured way. So you can have long-range correlations which are very structured, which are very easy to simulate. And a good example would be the sorts of things that appear with Clifford circuits. Clifford circuits have a huge amount of correlations, heaps of long-range stuff, which you can't really, which you don't necessarily see with local circuits classically. However, it's very easy to compute such things, generally. So the point is to try and generate long-range correlations in a very unstructured way. And these sorts of things we expect to be among the hardest sorts of circuits to simulate classically. Okay, so the first such example of this sort of problem was that given for boson sampling problem proposed by Alex Arkhipov and Scott Aronson. And so they established a potential advantage over classical computing for sampling from random linear optical networks. Really importantly, this advantage holds for the case of approximate boson sampling. So what they managed to show is that if the goal was, if you had a classical sampler which output probability distribution R, or output samples from R, whereas the ideal circuit was outputting P, they showed that if you could get R to be within a constant 1 norm distance from P, generally for growing system size, then crazy things would happen in complexity theory, up to a few conjectures that are still unproven. Okay, then a few years later, we proposed the IQP sampling problem, which was an improvement on boson sampling. In that, we basically mapped the problem to an interesting family of quantum circuits. So we took it from being a thing about bosons to being a thing about spin systems. But in doing so, the problem actually became a lot easier, it turned out, which made it much easier to generalize to other models. Okay, it is the way it's defined is in the quantum circuit model, and just broadly, the IQP sampling problem is that you start with the all-zero state, you apply Hadamard gates to everything, then you randomly choose from a circuit well, a family of circuits which are diagonal on a Z basis. You apply Hadamard's to everything again, and then you just measure the outputs. It's a very simple sounding problem. But all the sort of magic is in when you randomly choose these circuits here. Okay, so one of the other advantages of moving to this model is we could actually close one of the conjectures which is open for boson sampling. So that conjecture doesn't exist for the IQP sampling model, which left only one conjecture open, which is significant, and that problem is basically that the average case complexity of computing one of these output probabilities is equivalent to the worst case complexity of computing one of those. But I'm going to explain a bit more about that later. Okay, so one of the best known generalizations of this problem was the Google proposal for random circuit sampling. So this did a bunch of things. A lot of stuff was going on in this paper. But from a theoretical viewpoint, or from a computer science viewpoint, what they introduced was this problem of thinking about using something like a T-design or a Porter-Thomas type, or a random circuit which generates a Porter-Thomas type distribution for arguing that such circuits can't be classically simulated. Very roughly, what the proposal was to have something like around 49 qubits and 7 by 7 ladders, apply Hadamard's everywhere, a bunch of CZs, a bunch of single qubit gates, a bunch more CZs, a bunch more single qubit gates, and so on, for a depth of up to around 40 qubit, depth of up around 40. And if you had sufficiently high fidelity on those things, on all those operations, then you've arguably performed a computation that couldn't be performed classically. In that paper, we also introduced the notion of cross-entropy benchmarking as a way of establishing the validity of such a computation. There's also heaps of numerical testing, which is also one of the really interesting aspects of this project. We really looked at the difficulty of simulating such circuits in heavy supercomputing style systems. Okay, now I'm going to introduce a little bit of complexity theory, a little bit more complexity theory to get into explaining how some of this stuff works. All right. So what do quantum computers do? Quantum computers output strings X from things defined like that. Okay? It seems really simple, but it's a good point to start. What quantum computers don't do necessarily is compute that P of X. They output the X's with some probability which is defined by some unitary U. Okay? So the output of a quantum computer, okay, so the input, well, one way of thinking about quantum computing is that you input some classical description of a unitary and something you want to measure, which is polynomial in n. Now, so the output, the computation, will be some output probability distribution R of x, or x from R of x, in time polynomial in the size of the description of u, and the inverse of the error. Okay, so you can talk about ways of defining the complexity of quantum computing, or complexity around the probability distributions that define quantum computing in a bunch of different ways. So you can quickly get an upper bound in quantum computing power, which comes from, if you were to look at computing this output R of x, in the case when R of x equals P of x, then the complexity theoretic upper bound is a class called gap P, which is a very powerful class. We don't expect that quantum computers can actually do that. It's just that these probabilities are somehow like part of the model. It's just something which quantum computing inherits their complexity from these probability distributions. Now, BQP, which is a set of decision problems solvable on a quantum computer, can be defined by the set of things which are output by a sample x, such that the distance between P and R is less than epsilon in 1 norm. And if the goal was to compute R of x to 1 over polynomial additive of errors, then that's also equivalent to computing something in BQP. So these are just interesting things. So a few other things you can think about is SAMP BQP, where now instead of having a single bit output, you're going to take in a bit string as an output. Okay, and there, again, you define the accuracy to be to within 1 norm distance, like constant 1 norm distance, and you get the class SAMP BQP. Okay, and then the other two, I guess, important notions, which for this talk is the idea of a multiplicative sampling error, where you have an output bit string x again, and you're going to define a relation like this between P and R. And what you can show is that the complexity upper bounds that there's no classical R of x unless polynomial hierarchy collapses to the 3rd level. And finally, you can consider the output to be R of x such that it is close in relative error to P of x. And that problem is gap P complete. Okay, that was a really quick crash course. I'm going to show you this in pictures a bit more clearly now. All right, so we have P of x up here. We're going to talk about the complexity classes associated with it. So the goal for this set of problems is to bound the complexity of producing samples x by the complexity of computing P of x. Okay, so in the case of exact quantum probability amplitudes, you really only have two choices as to what the probability, or as to what the complexity of these problems are. It's either up here, like it's either P to the sharp P or P to the gap P, complete, or it's down here in P. And they're really the two examples that you get for families of problems like this. Okay. If the problem is to produce a 1 over polynomial approximation, then it's BQP complete. And that's the best you can hope for from a quantum computer for computing such functions. Now, you might actually, that's in general. You can actually produce better approximations if you know more information about the thing. If the only information you know is the circuit, that's what you get. Okay, so the last bit of sort of complexity theoretic jargon I have to introduce you to is this notion of sharp P and gap P. So sharp P simply counts the number of inputs to a polynomial size circuit that evaluate to 1. Okay, so imagine you have a poly-sized classical circuit. It can evaluate to 1 or 0. What we're going to do is just, given a circuit, you want to know how many inputs evaluate to 1 for that circuit. And that's a very powerful class. And gap P generalizes that notion that allows you to take additions and subtractions and such things. Now, in the exact case, there isn't a lot of difference between sharp P and gap P, except for like definitional things. But when you think about approximations to these functions, to these sorts of problems, it makes a big difference whether these things are close under addition and subtraction or not. Because if you have a very small error, like it can be sort of incorporated into gap P, but it may not be incorporated into a sharp P problem. Okay, so I said that on this slide as well. So one of the interesting things about gap P is that relative error remains, gap P hard problems remain hard under relative error approximations. So there are classes of F, like this, that stay gap P hard even under approximation. So you introduce this notion of error, it stays there. However, for sharp P, that doesn't happen. It ends up going down here or even down, or it becomes efficient classically even. Okay, so the reason for that is an algorithm from Larry Stockmeyer which showed that you can get a relative error approximation to any function in sharp P inside this complexity class BPP to the MP. And it turns out that this does not work for gap P unless the polynomial hierarchy collapses. Okay, so when you see such a stark difference, okay, for something which is naturally involved with the quantum circuit, the first thing you want to do is like try and use that difference, and that's what a bunch of us did. So Turhan and DiVincenzo in 2002, and then us and also Aronson and Arkhipov back in 2010 showed the gap P hardness relative error approximations of quantum circuit amplitudes for constant depth circuits, IQP circuits, linear optics, and any family, any universal for quantum computations by selection. For any of those things, we showed that there is no efficient classical algorithms for simulating such circuit families to within a multiplicative error bound without a collapsible polynomial hierarchy. Okay, so that's sort of the basics. But where things got really interesting was when Aronson and Arkhipov realized that if you ran this sort of argument with randomized circuits, or in their case with randomized linear optical systems, then you could lift this sort of argument from being a thing about multiplicative error bounds, which are completely unphysical, to being about normal notions of distance that we use in quantum computing all the time. In this argument, the quantum random circuit sampling argument, it showed that if there exists sufficiently accurate, efficient classical samplers for the outputs from sufficiently random unitaries U, Stockmeyer's algorithm can be used to approximate such functions, which could in principle be gap P hard. So there was a number of big leaps which got to that point, and I've swept like a huge amount of detail under the rug. Now, the really important part of this was the introduction of a random circuit. The reason why that's so interesting is because under this randomization assumption, the fact that you've actually got a random circuit, you're able to show that if you're close in one norm, Stockmeyer's algorithm will actually deliver you a relative error approximation. Okay. Now, to do this sort of pictorially and have a sense of what was actually shown, if you have some family U of X, we're computing the output probability of sharp B hard, even up to relative error approximation in the worst case. You can imagine like drawing a big blob here, which is that family. Now, what this argument showed was that if these output probability distributions have a product they call anti-concentration, which is essentially saying that they're very random, but they're not like completely random. Okay, so there's some, imagine having like an almost flat distribution, but with a small amount of polynomial wiggle over the top of that distribution. It's that kind of probability distribution. So it's got a lot of subtle differences across it, but it's still very, very random. So that's the property of anti-concentration. Now, the other part of this argument, if you can show that approximations to these output probabilities are as hard as, for random choices from within this family, if approximations to the output probabilities for the random choice are as hard as for the worst case choice, then if it has that property as well, then you, for a sufficiently large fraction of that set, then you should get an overlap. And then if you get a heavy overlap between these two families of things, then if there are classical simulations of these families of circuits, then that implies a polynomial hierarchy collapse. So in short, if the average case complexity is as hard as the worst case complexity, you'll get an overlap for these sorts of things. What we can actually prove right now is a situation that looks like that. Okay? So what you can do is identify families of circuits where you can show that anti-concentration exists. You can show that the worst case complexity is gap P complete. So relative error approximations are gap P complete. But what we can't show is that approximations to the average case happen on average, are also gap P complete on average. So that's the thing which is a big open question. This year, there was a really big result from Boulon, Pfefferman, Nurka, and Vazirani, who showed that in the case of exactly computing these output probabilities, the average case and the worst case complexity overlap for many of these classes of random circuit sampling arguments. So that was published in Nature Physics in sort of late 2018. Unfortunately, this isn't quite enough to prove the theorem that we actually want. What it shows is that we have a situation like this where for most things, the the complexity of exactly computing a randomly chosen circuit amplitude is sharp P hard. Now, what we want is this to be approximate, because that's actually what Stockmeyer's algorithm spits out as an approximation, not the exact thing. And we need that to close this loophole on this argument. But what was really interesting about that was that it actually gives us even more confidence that these conjectures that people have made are correct. So ultimately what we need to do in boson sampling, RQP sampling, and these other things is actually make a conjecture that these two things overlap. And that's an open problem. This has been partially closed, but not completely closed. And completely closing this problem is likely to be significantly difficult. Now, what families of circuits actually have these sorts of properties all at the same time? So there are quite a number of circuit families being shown to have sharp P hard amplitudes and anti-concentration at the same time. And these proof techniques sort of fall into sort of three categories, especially if we're showing that they're sufficiently random. The first is direct calculation, where there's a really easy representation to work with. So that was what was true for IQP circuits. The second was using the theory of k-design. So that's a way of characterizing approximately random circuits. And what's been shown there is that hard circuits are randomly chosen from circuits that are from either universal gates or conjugated Clifford circuits, and that's been shown over the last couple of years. And the third case is to use measurement or post-selection gadgets to demonstrate anti-concentration on a subset of the output qubits in the system. All right, so let me talk you through IQP sampling and the properties of these sort of problems that lead to, well, on the complexity theoretic properties of the problems underlying the complexity of IQP circuits. So as I said earlier, an IQP circuit looks like this. You have Hadamard's diagonal Hadamard type circuits. Now, for every IQP circuit, actually, you can find a representation of an output probability in terms of an Ising model. For most IQP circuits, this is actually quite a simple thing to do. It's very easy to do when you only have 1 and 2 qubit gates in this diagonal part of the circuit. what you can show is that you have an Ising model, which is like the Ising model you've probably all studied in undergraduate, where you have vertices, you have edge interactions, and vertex weights, which correspond to like an external field in your Ising model. So you'll have some Hamiltonian, which is defined by a graph. And for these family of problems, where you randomly choose a circuit from T and square root of control Z gates, you end up with a Hamiltonian here with edge weightings given by, well, these quantities up here. So you have like, WE could take values from k pi over 8, where k takes values from 0 to 7. And so when you randomly choose an edge weighting, you randomly choose a value from 0 to 7. And for the vertex weights, you do a similar sort of thing. This is from 0 to 3. And then what you can show is the output a circuit amplitude for such a model looks like the partition function, or complex temperature partition function of such an Ising model, okay, where V here is the number of vertices in the graph. Okay, so this isn't dramatically complicated in the case of IQP circuits. You can quickly work out that this is what you get by just evaluating the trace of like, well, evaluating what that circuit amplitude looks like, okay? For universal circuits, it's a little bit more complicated, but it's been known for quite some time that if you take an arbitrary quantum circuit and you take an amplitude, there's a way of expressing that amplitude in terms of a classical Ising model, a complex temperature classical Ising model. In the case of the Google proposal, where we start with like a 2D lattice, have these CZ-type gates and then single qubit unitaries applied at random and so on, what you actually get is a quasi-three-dimensional Ising model. And each amplitude is a different quasi-three-dimensional Ising model. Now, moving forward, what's the complexity of Ising models? So this has been a huge area of study in classical complexity theory over the last 20 or 30 or 40 years. And really interestingly, this area of research has exploded in the last 5 years, because there's been some major breakthroughs in terms of understanding the complexity of approximations to Ising models. So some of the really big results, so way back in '93, Jerram and Sinclair showed that along this line, there's always a good classical approximation to the Ising model. So that's for, you take an Ising model of the type I was just talking about, and we're going to look at what the edge weightings can be in the model. And you can show that along this real axis here, there's always a good classical approximation, which is efficient. Okay, that was a major breakthrough back in '93. Fast forward a long way, and there was a bunch of breakthroughs about 5 or 6 years ago. What was shown was that actually you can define a region along this axis, where we didn't understand things very well, where we can find that there's actually a phase transition here in the behavior of the model. So everything to the left of that dot, the problem becomes sharply hard to compute. Everything on this side of the line, there is an efficient classical approximation to this model. This year, myself and Ryan Mann, and also sort of independently, Lou Sinclair and Shrivastava looked at the problem of extending a result of Patel and Rex to look at, well, the complex version of this problem. Okay, so they showed that there's a region here which matches up with these earlier results on the phase transition. So they looked at a region around that real line, and we looked at this region here and showed that this region demonstrates a classical approximation for everything in that space. What I'm effectively saying here is that imagine you have a bounded degree Ising model, which is the sort of thing that we have occurring in quantum computing, and you want to consider small time evolutions around that model. We showed that there's a classical approximation algorithm for computing the amplitude of one of these circuits, so long as you're in the regime which is like 1 on delta, where delta is the maximum degree of that graph. Okay, and interestingly, there's a little gap here which gets you to sharp p hardness occurring in the complex case. So this is an omega 1 on delta, and it's a big O 1 on delta, and there's a constant gap between there, and we're working right now to close that gap. But all the supremacy stuff lives up here, essentially. And then when you get inside this regime, it becomes classical again. Okay, now why is that? Well, it's complicated, and I'm not sure I can get into it time-wise, but essentially, we think the reason comes down to post-selection. Now, all of the arguments I've talked about today, there's a common thread that's running in the background, which I may not have explained very well, but all of these models have the property that they're either universal directly, or they become, all these circuit families are either universal directly or they become universal with the addition of post-selection as a trick that you can use. Okay, so post-selection, the act of disregarding all but a desired outcome from some probability distribution allows you to rescale probability distributions in nifty ways. Okay, so the sorts of things which occur a lot, you see a lot of expressions that look like this, where you post-select on the all-zero outcome and you get 1 over some exponential times the probability of something. Now, what's interesting about that is that this quantity on the left can be easily computed, whereas that quantity might be quite hard to compute. Okay, so the complexity of relative error approximations is maintained under post-selection, which is a really important property. And this technique was used originally by Tuchel and DiVincenzo in 2002 to show the complexity of multiplicative approximations to quantum circuits. And is at the heart of most supremacy proofs, actually, for two reasons. Firstly, this thing about relative error approximations, and secondly, anti-concentration emerges also when you post-select in the right way. Okay, to give you an example of that, imagine you wanted to take a random circuit, like the Google-type proposal. Instead of doing the random circuit, one of the things you could do is take a really big cluster state and randomly measure qubits, like where you just let the measurement randomness take care of the fact that on this output thing, you will just end up with a random circuit. So this is a general idea which actually is at the heart of several proposals for demonstrating quantum computational supremacy, and was first shown by Gao et al. In this paper in 2016. And essentially what they do is flatten out one of these circuits. And this works because of this post-selection trick. Now, a few slides ago when I mentioned this is a classical approximation scheme for small time evolutions of Ising models, the reason why there's sort of a threshold here is that you can't post-select your way into this hard regime when you're in that small time evolution regime. Okay, and so many people have extended this result in many different ways. And I guess the really interesting ones, the ones up here, you can just look at, Boson sampling's up here, where they showed they don't have this anti-concentration property, but they do have this exact average case hardness property. Likewise, the Google proposal, which is down here, and that was shown. The exact average case hardness property was shown here. Okay, and there's been a whole series of proposals around such schemes. Now, I'm running a bit out of time, so I might fast forward a bit. So you might ask, is there some sort of trade-off between what the depth of these circuits needs to be and to also see this sort of supremacy kind of behavior? And the answer is yes, there is. So loosely, it comes from tensor network algorithms. So if there's a tensor network algorithm, so imagine you have a 2D lattice. Tensor network algorithms can compute any output probability that looks like that in time, which is a minimum of 2 to the order n, where n's number of qubits, and time 2 to the little d times big D, where big D is diameter and little d is the depth of this model. Okay, so that's just a simple thing that comes from Markov and Shi back in 2006. So imagine you have a sub-square root n circuit for a set of circuits we call sparse IQP circuits. Then what you'll find is that the output probability can be computed in sub-exponential time. Now, this contradicts another known fact, which comes from the exponential time hypothesis, that such output probabilities actually seem to require exponential time to be computed. So we talked about that in this paper, but also Huang, Newman, and Segedy talked about this year and showed that. More generally, there's going to be a time-space trade-off between depth and the size of a circuit, okay, for these sort of supremacy problems. So if you wanted to go to sort of sub-square root n depth, you won't be hitting, on average, the same random set of problems that you would if you're at higher depth. So what I'm trying to say here is that in order to simulate a random 50-qubit thing in a cluster state, like in constant depth, you need something on the order of 2,500 qubits. Okay, so there's a necessary trade-off between time and space here, which is actually an essential ingredient in all of these proposals. All right, so going back again, so where is this quantum frontier, right? Where is this boundary between classical and quantum computing? It can't come directly from these complexity theoretic arguments. You actually have to look at the actual run times of classical approximation algorithms. There's been a ton of work on this in the last 2 years. I'm not even going to do any of this justice talking about the large amount of work that's happened. But very broadly speaking, there's been a lot of work on tensor network algorithms for efficiently computing quantum circuit amplitudes. A general theme of the best work among all of this is looking for ways to find symmetries in a given quantum circuit. That might mean, is there ways of finding a whole bunch of diagonal gates that we can contract the tensor more efficiently with? Or on the flip side, it's like, can we work with a symmetry imposed by a noise model that might be present in a given quantum circuit? Have a look at some of those references. There's tons of really good ones. I particularly like this recent paper. That's not it, that one. 1811 09 599, where they did a really good job of trying to summarize all the work that people have done. Okay, but roughly the answer is still around 50 qubits. That's essentially the answer. Like, give or take, what type of gates you choose and like what the depth is. Around 50 qubits, around depth 40. That seems to be roughly where things begin to get really hard for classical computers. Now, I'm going to sort of speed through this really quickly, but I just want to give you a sense of what can happen when you do have take noise into account in these problems. So we showed back in 2016 that actually when you add a simple noise model to these IQP circuits, like you essentially get a quasi-polytime algorithm for simulating the output distributions of the noisy version of that circuit. So instead of this behavior, you actually get a line, okay, for the classical simulation of the realistic system. Well, realistic. For a noise model that isn't actually that realistic. So we just considered measurement errors at the end of the circuit, and there was no other errors in the model. And the way that worked was by exploiting symmetry in the noise. Essentially because we knew that these circuits would always be diagonal, you can show that under that error model, you get in the Fourier transform of this output probability distribution, you get exponential suppression of correlations in that model, which makes it quite a lot easier to simulate. You can construct then an algorithm based around that to show that there's a classical simulation for such problems. This was extended to the random circuit model by Gao and others in this paper, and you can actually also show that, and also interesting, you can show that when you're in the regime where you actually are punching to B for supremacy, i.e. that the fidelity of each individual operation in your circuit is roughly like one on the system size, such algorithms necessarily always perform exponentially badly. So it's kind of interesting. Like, the realistic scenario is that noise just keeps growing as you increase the size of the system. But if you introduce a cutoff and a bound, and you can show that the classical runtime for such algorithms will always be bad if you've got sufficiently low fidelity on each of your operations. Okay, that brings me to a couple of things we don't really have time to talk about. You can introduce notions of semi-classical error correction, you can get rid of that noise. And I just want to, sort of basically end on what I think is probably the really interesting part of this, where this work is going, which is there was a really big breakthrough this year, generally in the theory of quantum computing, which was that they showed that, well, Emil Amadev showed that you can do blind verification of a quantum computation with a completely classical verifier. So the verifier essentially can construct circuits in such a way, or can give descriptions of circuits to a quantum computer in the cloud somewhere in such a way that we can verify the computation they did. And the trick was basically twofold. The first realization was we don't need to actually completely confirm the entire computation. All we need to do is to confirm they actually did the circuit they claimed that they were going to do. The second step was to introduce the use of post-quantum cryptographic techniques in order to do such an encoding. And I strongly recommend you have a look at that paper. It's excellent and well worth looking at. But that brings me to my sort of final part of this talk, which I'm really running short on time to talk about, which is that I think one of the most interesting prospects for demonstrating in the near term that quantum computers can outperform classical computers in a verifiable way is through the use of pseudo-random constructions. Okay, so introducing notions of cryptography gives us a way of interpolating between these very random structures used in these random circuit sampling arguments and the structures that we saw in the Bravi, Gossett, Koenig paper, which weren't random at all. Well, weren't particularly random. Okay, so introducing notions of cryptographic schemes gives us a way of getting between these two extremes. Okay, thank you very much.